I'll stop the recording. The recording is in progress. Kunal, take it from here.
Okay, awesome. So let's go through the agenda for this breakout room. To bring everyone on the same page, we will go through a quick recap of how to use Qiskit Metal, how to set up EPR analysis for our example, and understand the results. And my aim here is to really drive forward the problem statement that we have been working on. That is to how we want to automate this iterative process for optimizing different parameters. And after that, we will go through the QDesignOptimizer file structure again and how to really understand one of the tutorials that we have set up for you guys. To begin, I am using one of the tutorials that is provided by Qiskit Metal. It is under tutorials, analysis, and we are looking at the eigen mode and EPR tutorial. It is one of the more useful or mostly used tutorial that you will find in this notebook. We sort of assume that you have, you know how to create your design, etc. But we will still go through that part of the code again. So when you try to set up any simulation in Qiskit Metal, the first thing you're going to do is create your design. The first step is really to specify how big is your chip. In this case, we work with a planar design, which is say any 2D superconducting chip. They do have more options for a flip chip or multi-planar architecture, but for our purposes, we will stick with the planar architecture. There are a bunch of components which Qiskit readily offers. One of them is the popular transmon qubit, which is what we are going to use in this study. With Qiskit, you can just import these components readily and add them to your designs. And once you have your design ready, one can import a EPR analysis for doing a simulation of this design. So far we have only created a design. We have imported this EPAR analysis, which comes with its own render. And the render is going to now translate this design that you have created, a very simple transmon qubit, into something HFSS can understand so that you can run this EPR analysis. A typical simulation setup looks something like this, where you're going to specify how many modes I want to look for, how many passes I'm going to perform to really see the convergence of this simulation. There are a few variables which you can set up, but once you have all of this ready, you can really just run the simulation and it will ANSYS, Qiskit Metal readily connects to ANSYS and sets it up for you. So you really haven't done anything with ANSYS so far. You created everything in Qiskit Metal and now you have rendered it and running it on Qiskit on ANSYS such that you can now see the results of the simulation. If you, okay, we will not go through the output of it, but if you look at your ANSYS window now, you will find something like this. In this case, it's a CPW or a root meander with some wire bonds, not a transmon pocket that we created for design. That is because all of that was done here. But once you have this, now what you are going to do is you are going to look at the frequency of this simulated mode and how is the mode distribution present across this structure that you have created. Now, say you wanted to design something around 7 gigahertz or 8 gigahertz, but after simulation, you find that this mode has a frequency of 9.63 gigahertz, which is not great. Now you want to update some of your parameters such that after simulation, you find this frequency to be around your intended frequency. Let's say example 8 gigahertz. There are a few questions. Okay, we can take questions later. So now this is where you are going to do the entire setup all over again. You have to go all the way up, set up this design again. Then you are going to set up this simulation again and run the simulation on ANSYS to find has this value really changed to 8 gigahertz or something closer. And this requires a lot of manual intervention. You have to set it up repeatedly. You have to give a very good guess of how much the parameter should be changed so that the simulated value comes closer to your design value. And this is really the part that we have automated by creating a file structure like this. So we basically broke down the Qiskit metal and ANSYS simulation into a few different components here. We have the design variables, which contains all the parameters that you are going to tune. We have something that creates the design itself, and we have a file which gives unique identifiers to all the Qiskit components. All this part here really creates the design that you want to work with. And once you have this, you can then send it to our optimization or simulation driver. To really get the simulation driver working, there are a few more things you want to put together. That is the mini studies, the optimization targets, and the parameter targets. When you set up the optimization target, this is where we link the physics of how the dependency of that optimization target is to our simulation. We will come back to this again later. So this is really the idea of how the file structure has been set up. If you look at our file structure here, you will find that I have a project folder in which we are going to look at this coupled transmon chip example. And all these files really sit in that folder. And now they're unique to this project that I'm going to run for you guys. Any questions so far?
So in terms of design, Kunal, so
Yes.
all the designs we do using the Qiskit metal,
Yes.
whether by using their available library, from their available library, or
Yes.
whatever design change you want to make, to do by yourself. So in the optimizer, we don't have that ability, right? Like
Uh,
predefined um,
so
structures, basically.
So there is a bit more flexibility there because this design can also take a custom component that you can create. The only thing it has to do is somewhat follow the norms of Qiskit Metal design. If you look at Qiskit Metal tutorials, they do show you how to create a custom variable, a custom component that you want to work with. The key thing here is that now, if you use something like a design variable, you get to have a variable instead of putting a constant to your values, let's say the transmon pad width or the transmon pad gap. You are going to give it a variable, which is what we are going to update when we run this simulation. So the simulation is independent of design. All it cares about is these values of design variables, and the design can be parameterized according to what your study is, but you do have full freedom on what this design can look like, and it necessarily doesn't have to be a Qiskit component. You can create your own component for this. Okay, we can take more questions going forward, but let's get into the code. So the first task is to create the chip, right? And if you go into this, you will see that it really defines the material, the size of the chip, and it calls in a Qiskit uh, function, or this is the design class which Qiskit gives to design your 2D planar architecture. And now with these variables, we have kind of modularized what this input parameters can be. And you want to have this override enabled equal to true. so that you don't always delete the component every time you want to update the design. One of the key thing about this architecture is that if you see here, this part of the code updates all the mm, values for the design from the JSON file that will create for your design parameters. And this basically completes this part of the loop where you have a bunch of design variables and you have assigned them all in your design and created this design using the Qiskit design library. Once you have your design ready, there are a few things you have to set up to really get going. Some of two of these are the mini studies and the optimization target. If you look at our mini study library, you'll find that there are a bunch of these which we have already written for you guys to play with. And what they pretty much do is they need you to provide the modes and the parameter targets to run a mini simulation of these components. Let's understand better what that means. So this is kind of the circuit that I have created for this, that we have created for this tutorial purpose. And the mini study really now takes in few of these components. Let's say this resonator coupled to this qubit, and it's going to simulate the dependency of parameters between these two. And then it's going to take these two components and simulate them together. So it's really breaking down this whole circuit into smaller individual parts, which you can simulate much faster and then put them together to look at the interdependencies of these parameters. And if you now see what the ANSYS results look like. Okay. Okay, this doesn't look as good as I thought it would. But here is our ANSYS mini study that we ran the last. And if you see this, it really has now, the last thing it has simulated is a resonator coupled to this qubit, which is just a smaller part of one of this circuit. So with this mini study setup, you are going to simulate the whole circuit in these smaller blocks by giving the modes you are interested in and the parameters that you are going to use to run this mini study. Any questions here? Okay, we can.
I really want to highlight here that this mini study allows for very efficient simulations of subsets. And we've, from a user experience, we've built a 12 mode or 13 mode quantum processor, and it was very efficient to break up this big problem into smaller sets, and then afterwards create mini studies to look at the coupling between the mini studies that had been stimulated initially. But yeah, this is a nice way to set up the simulations essentially.
And also make them much faster.
Yeah,
instead
absolutely.
of simulating the entire chip. But okay, once you have the mini studies set up for your design, let's look at the optimization target. Uh, the optimization target really takes in what are the parameters that you want to optimize for in your simulations. In this case, we have the qubit frequency and harmonicity, then the resonator frequency and the kappa. And then we also look at the resonator qubit chi, which is really the interdependent quantity here, where this quantity, it depends on many different parameters. For a qubit coupled to a for a transmon qubit coupled to a readout resonator, the dependency is quite complicated, right? It is more or less like this. And if you have to do this now manually, you will have to run this simulation quite a bunch of times to get a really good convergence on the chi value. because every time you change any parameter, you're going to change the detuning. If you change the transponders, capacitor pads, you're going to change the EC. And simulating for a very good value of chi makes it a very challenging problem because of this interdependency. And in our simulator or our optimizer, we have really optimized this by specifying the physics of these relations. The physics really goes here where you give in some relation. It doesn't have to be a very accurate relation, as Axel pointed out to you guys. It just have to have the correct form. And what the optimizer will do is based on these increments that it makes to these parameters, it will try to reach a convergence based on this, and the updates are based on uh, this relation here, which is where we are encoding the physics. So the optimization target really takes the modes that are involved in optimizing this target parameter, and it also takes in the design variables that you need to make these updates to the parameters. There are a few constraints that you can assign, but this is really where all the updating of the parameters and rerunning the simulations iteratively gets automated. So once we have the mini studies and the optimization targets set up, we have everything we need to go forward. Then you will set up something called a design analysis, which will take which takes in a design analysis state, which is the design, the renderer, and the parameter targets that you need to run the entire optimization. It takes in a bunch of mini studies that are relevant to this example and a bunch of uh, other things you need to make sure how the variables are getting updated correctly. But okay, so far we have set up our optimization. We know what is our target parameters. We have set up the mini studies. Are there any questions so far?
I don't see questions in the chat, but
I have a question actually. So, how relevant is this mini study for example, let's say single qubit design? So, let's say if you change like very small design parameter in your qubit, for example, the size and shape of the junction or extra bit of metal coming towards the junction, etc. So, do you
Yes.
still need to do the mini study, or you can just run the entire simulation at once in terms of efficiency?
In that case, I believe the mini study is not very relevant since it's only one component. So you will just create, say, a mini study with that component, and then it doesn't try to break it down into any such coupled components or pairs of components. It just takes that component, tries to update the variables based on our definitions, and tries to see how the dependency is changing. And it will still anyway happen in this design analysis that where we have provided this mini study. So for a single component optimization, it's not very relevant, but since we going forward want to study more complicated circuits and really break these down into smaller pairwise component simulations, that is where mini studies really uh, do the magic.
no. I would like to add here that the mini study essentially sets up your simulation. You specify what the mesh is going to be like. You set up um, what the plotting is like. You set up what the ports are like. Um, and
The
what the
junction.
junction is like. So in this regard, you kind of need the mini study, but it is not that the mini study actually breaks something down. So the word mini study is somewhat misleading here. Um, it is more that you can think of it as the simulation setup, like which components do you want to simulate, yeah, and this is then taken forward to the design analysis. But yeah, it's I think it's a good question, and I think does that help you? Does this answer help you?
Yeah, I think that's good.
Thanks.
Thanks.
Okay, so let's move forward. Once we have run this simulation, then you're going to see the typical ANSYS output, or the output you see in a Qiskit Metals tutorial as well. It will explain you, or it will output what is it that you have set up, how many passes, the number of modes that you're looking for. Then it does the connecting to ANSYS part. And now to run the simulation, we are going to do two things. We are going to, so we said that we want to run this optimization driver a few times, right? So this is where we specify, say, number 5. So we are going to run this updating variables 5 times. And in each of those simulations, we are going to let ANSYS do 4 iterations to really converge on the simulated value. So if you look at what is the output of this, you'll see that these are all the design variable values that we have uh, assigned to different parameters of the design. Then it's going to run a eigenmode study. It's going to give you the final values. Let's say here. But now this is where you see that we are going to update the variables here again, and we are going to start the next iteration of this optimization. And this will happen a few times based on how many passes runs you wanted to do. And it's going to keep updating these values over and over again. And to see the final result of this whole exercise, you will see that our most complicated parameter, which was the resonator qubit chi, really starts converging to our target value with a few iterations of this optimization. So we gave it 5 passes, and by pass 3, it was quite close to what our target uh, chi was. And then it has saturated quite well for at this target value. For our other parameters, we do see that 5 iterations was enough to also converge our resonator frequency value to the target value. The kappa simulations they are saturated, they are quite close, but we still have a lot of work going on them. And even the qubit frequencies have converged within 220 megahertz of the target value. So with this, we sort of see that within 5 iterations, our optimization has updated the parameters correctly to really reach the targeted parameters that we specified for the qubit frequency and the anharmonicity. We can run a bunch of post analysis on these results to gain more information from our results. If I have to show you the, so this is what happens in one single pass of the optimization, right? So we said run it 4 times or 4 iterations. So we see a good convergence in a single simulation. And this 4 convergence, it's what we have ran then 5 times uh, to get our optimization. So this is a single simulation, and this single simulation is what we ran 5x times to uh, to see these convergences to our targeted parameters. So this was a very simple example. Do you
I,
guys have any more questions?
I quickly would just want to add for clarity. So we need to distinguish between runs and passes, absolutely. And we've chosen here for the example a small number of passes, like 4. But for eigenmode simulations, that's often insufficient. If you want to get accurate results, you need something on the order of like 10, 12 passes before it becomes a stable solution. In some cases, you need to go up to 20 passes. Best is to look at the convergence plot in ANSYS, and then you know whether the number of passes was sufficient or not. So what Kunal is showing here, for example, is one option. Yeah, so you look really at the result, at the frequency evolution of the mode, the real part of the mode 1 and the real part of the mode 2 in green and red versus the number of passes, and you see, it's converging already. But maybe if you look at the detail, there's still a 10 megahertz shift or so. Depending on the precision that you need in your design, you might need to increase the number of passes then. Just keep this in mind when you run your own simulations. And then as for how many runs, yes, this depends on how fast your entire optimization converges. But there are two convergence criteria here. One is on the design variable, and one is on the design variable inside of a single simulation. It sometimes takes a moment to grasp it, but so that's why I'm dwelling on it once more. That's my comment here at this point. Is there anything else about the simulation setup or optimization setup here? One thing that I could give you as a trick that also Axel discussed before during the talk that he gave. Kunal, if you go back to the optimization setup, I want to
Ah,
give people an idea of how to improve the simulations and make them faster a little bit.
okay, sorry, it's here.
Yeah. So if we look at this optimization step, we specify a fixed number of passes for every run. But what is actually beneficial is if we update the number of passes in every run um, adaptively. So we start from a low number of passes, and then with every run, we increase the number of passes. So we start from something coarse and then converge to something that is finer and more precise, but then the simulation also takes longer. But we found this to be a nicely working solution. So if Kunal was typing in now plus I here or plus 2I, yeah, then we would start with 4 passes in the first run, and we would go to 6 passes in the second run, and so on and so forth. And this will make your simulation typically converge a little bit faster. Just to give you an idea on how to get started efficiently.
Just to be clear myself, which one defines the mesh size here for enterprises? Is this delta or the passes itself?
With every pass, the mesh is updated in ANSYS, and where
Ah,
can we go back to the optimization step? Yeah. So with every pass in the analysis, the mesh is updated, and you can actually output the mesh after every adaptive meshing step, and you see that it gets denser and denser in the regions where the field is strongest. Now, the delta F is the abortion criteria for the convergence. So say you've specified 20 passes and your convergence criteria is the criteria delta F that's specified here, 0.001, but your simulation already, reaches this precision, this convergence criterion earlier, maybe after 12 passes, then the optimization or the simulation is stopped there, and you move on to the next run, I plus 1, without simulating the remaining specified passes. So there are two different ways to move on to the next run, either by exceeding the number of passes or by reaching the delta F convergence criterion. So this is the difference between update number of passes and update delta F. Are there more questions about this optimization step? This is really the core of our optimizer in just a few lines of code. There's a lot of stuff hidden, of course, and maybe some of it you only discover if you use it yourself. Um, but we also don't want to overload you with details that you might not find relevant at this point. In those cases, I only strongly recommend you to reach out to us if you use it and face questions. We tried our best to make the online documentation as clear as possible, but of course, everyone reads it differently. Here's the online documentation. There's a Optimizer 101 where we go through the concept again. Basically, the entire presentation that you've seen today is based on this Optimizer 101. But we also have a user guide, which is just beneath it. And there we show you what steps need to be taken uh, in order to set up. If you click on project setup, yeah, here in the project setup, these are all the necessary steps that you need to take in order to set up your first own experiment. But if you find anything unclear, something doesn't work for you, we'd be happy to help you. Um, because at the end of the day, it's a small time investment from maybe from our side, but we would like to also, uh, so provide this service because we think that at the end of the day, it will just make our package better and
So
more
Lucas, there
accessible.
is a question. The question is, can I set the smallest resolution for the length between each run, since the e-beam writer has a smallest resolution that it can write?
That's uh that's an interesting question. No, the answer is we do not have a minimal change, a uh, delta length or so, yeah, as an convergence criteria. Um, I think I've never seen that the precision of the optimizer reaches this level of the e-beam precision, but yeah, you could think of optimization steps where this is possible. Um, let me say, mm, what do I want to say? Um, never
Is
mind.
it is oh, okay.
Uh, da, 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 da. Okay, my voice probably not important enough. Um, yeah, so the short answer is we cannot specify a minimal length between two optimization steps as a convergence criterion. Not at this point. I hope that answers the question. Are there more questions?
Mm, If you want to install the package, you can find all the instructions over here. You can install it by just doing a pip install, but you have to install the Qiskit metal independently again. But to really have access to our tutorials, you need to clone the GitHub repository, and you can also use the environment.yml file to create your own Conda environment and install this optimizer. That is one thing I missed in the beginning.
We actually tried our best. I mean, people that have been using Qiskit Metal in the past might know that the installation of Qiskit Metal can be very cumbersome because there are so many dependency conflicts that need to be solved. We really tried our best to package this design optimizer in such a way that you don't have to solve these conflicts yourself. Um, and how do we do this? We use a package that is called Poetry to resolve the conflicts uh, prior to your installation.
I definitely need to admire you guys in this. Actually, this was the simplest and very straightforward installation, as well as running very basic examples you have given there. So this is excellent. Well done.
Thanks for that feedback. It was an in it was a significant amount of work to get it here, and I wouldn't be surprised that if there's a bug somewhere, but if you find it, I'd be happy to fix it for you. Okay. Um,
Okay, then
More
if
questions?
there are,
Maybe if people are interested, we could look at a different example, for example, check a capacitance study. What do you think, Kunal? Is this of interest? Because sometimes people want to specify capacitance between two objects or so.
So I have two basic questions before we move on to that direction. The first question would be, let's say you did the mini study for different components, and at the end, how do you combine those for your entire circuit simulation? The number one question. And the number two question would be, I saw in your design, and almost certainly this is the case everywhere. So your nonlinear element, which is junction, qubits. So how do you put the actual junction design there later on? So you have to do manually later on, or there is a way to just make sure whether this is your Dolan bridge junction or Pict style, which is Chalmers' invention. So this type of junction. So how do you add those there and then extract the ZDS file for the fabrication ready chip?
I I can answer the questions. Kunal, do you want to answer the questions? I can take them. You at? Uh,
you
so
can go for it.
so let me start with question number two. How to integrate junctions? Um, this is best done by Qiskit Metal itself. For this, I would ask Kunal to go to the design of the transmon.
Design above the transmon.
Yeah, can you go to the render Qiskit Metal design? Yes, and now add transmon plus resonator. Yes, here here you see the options for the transmon design. Yeah. Um, so under hashtag make transmon, you find the options for the transmon in a dictionary. If you scroll a little bit down, a little bit more, stop here. You see an entry which is called GDS underscore cell underscore name. Yeah. And this is the object that you can populate during the rendering of the Qiskit Metal design towards a GDS file with your own specific junction file. And how do we do this? We typically draw by hand, or we've actually automated it. We draw Manhattan junctions as a GDS file, and then we load them with this specific name into the GDS file of the transmon as we render the entire circuit. This is how we can load specific junction designs, be it Manhattan or Princeton or Dolan, or there's any other junction design into the rendered GDS file. And of course, any other junction name can be placed here. Yeah. So this is my answer to your question number two. Question number one is on the mini studies. What do you do if you have a network of multiple qubits? Yeah. So maybe can I ask you to open the result, the design of the 2-qubit example, the GUI for it, the GUI output? Yeah, here. So your question essentially, if I understand it correctly, is which mini studies would you set up here in this example in order to obtain, a full simulation of the chip, right? And our suggestion would be to start with the single qubit resonator system coupled to a transmission line. So pick the top qubit, the top splitmon, the top resonator, and the feed line according to it, and make this one mini study. And the second mini study would be the similar circuit at the bottom. And once this is set, we would in a third mini study combine it all together. But since the parameters for 1 and 2 have already been set, and they are already very close to the target, we don't expect much of a change in the parameters for the subset of one and subset of two. Maybe it needs a small adjustment to the qubit in both cases, but the resonator and its coupling to the transmission line will be mainly unaffected. And if you look at the optimization targets, we can then deselect, for example, the specific parameter of which we think there's not going to be a big change. So if we go, for example, now at the optimization target here, yeah, Kunal presented to us this list which you can toggle from true to false here right at the top. So if we, for example, take the 2-qubit example, then we can, and this function here is basically a list of, or outputs a list of optimization targets for every parameter. Then you can basically choose which of these optimization targets you want to include in your study. And this would be my answer to question number one. So you break it up into mini studies first, and then you make a bigger mini study combining multiple of them or connecting them, depending on the circuit geometry that you use.
Thanks.
Okay, I have to solve some error there.
Do we have more questions about the eigenmode simulations of single qubits or multiple qubits? Otherwise, we could show you in the remaining time how a capacitance study looks like. It is very analogous to what Kunal showed you before, but there are teeny tiny differences which we could highlight to you if you're interested. And unless you object, we might just move ahead with it with our schedule. But yeah, again, if you have questions, write in the chat, raise your hand, interrupt us. We'd be happy to help you. Right. Maybe Kunal, you can go ahead with the capacitance
Oh, it
target.
got stuck here for some reason. It says it can't find n. But n
And
is defined here.
yes, maybe you need to restart your kernel or
Yeah, I did that. And then if I run it, it still gets stuck here. Okay. Is there a different example I can run?
import time. Can you point me to the place where it gets stuck?
Here, it can't find n in the mini study group.
It is interesting. Well, that's I guess
But that is
a
over here.
life hack. Um, this is what happens if you code live. I'm not sure. Maybe we clicked the button or deleted a line or whatnot. I have not
Yeah,
seen this. I have not seen this problem before in this particular example, so it's weird.
so it did this. Okay. And it runs this one.
Sorry,
Can't
let's
find it here.
try.
Yeah. Mm,
We could look at the charge line decay or the kappa target. Yeah, let's see if this works better. Sorry for this. This should be the same GUI output, but the design setup is different. Can we go back to the uh,
code.
code? Yeah. Okay, this looks better, right?
Yeah.
Okay, for everyone to get back on the page. So we are now interested in computing the decay of a mode in a qubit into a charge line that's connected to it. So really depict maybe a split mon with two islands, one junction in the middle, and this is in that is connected here to a charge line. Yeah. So split
Mm.
mon connected to a charge line. And the question always is how close can you come with your charge line to the qubit such that there's no unwanted decay from the qubit into the charge line. And one way to go about this is typically to compute the capacitance between the charge line and the qubit, and then use some formula to translate this into the decay rate or the T1 limit. Yeah. And for this, we also have an optimization where we can basically, specify what T1 limit we want to expect or we want to tolerate, maybe I don't know, 10 milliseconds or so, 1 millisecond. Depends on your implementation, on what you want to do. And then we can very specifically target this number with this optimizer. And
Okay, this
Kunal
might
is,
be that
yeah,
might be too long
this
to go
is,
into.
let's not dive into these details, Kunal. Let's go back to the example.
Yeah.
So what do you see in this example? It starts in a very similar way, right? We generate the design as we did before, right? Render the design, maybe you stay there for a second, show people. So we render the design in the very same way as we did before. The output of it looks like this. It's the full chip. And all we need to do next is to specify the mini study, right? Now we go back to the code and look at the mini study. Here, the mini study is ms.getMiniStudy qubit charge line. And what we do in this mini study is we specify the components that we want to consider, namely the qubit and the charge line. And we feed these components into the mode decay into charge line study, um, which is just the same again. We specify the mode frequency, the capacitance name, um, and the name of the qubit pins. And this is basically our setup for a capacitance simulation that we then run. And we take the output of this capacitance simulation to compute the T1 limit on the mode. Now, if we go back to
So,
the main example,
uh, Lucas, there is a question
there's a question.
here. So the question is, what is the equation we use to calculate the decay, and how does it compare with the black box quantization from Y parameter in a driven simulation?
Okay, I know the answer to part one.
Yeah,
I think I'm not familiar with part two. Or maybe I don't quite understand the question, but let's take it. Let's take question number one. Question number one is what's the formula that we're using? So we can
yeah.
click on uh, mode decay into charge line study. And here we have our get T1 limit due to decay into charge line. And what we essentially do is we take the capacitances. As you can see, we go a little bit slower.
Yeah, okay.
So we have this function get T1 limit due to decay into charge line. We get the names for island 1 and island 2. Then we take the capacitance CA0, CB0, CA1, and CB1 of in the Splitmon configuration of the island to ground, of the island B to ground, and between the islands. And this is CJ. And we take these four capacitances and put them into our formula, calculate T1 limit for floating transmon. And here, what you can see is we compute gamma for a mode decay into a transmission line, given the frequency. Can you go back once?
Oh, okay.
Yeah. We basically put the frequency, the capacitance sum, the coupling capacitance, and the charge line impedance into this equation. And eventually, this is just a product of all of
Should
the
I?
four things that I've just mentioned. So yeah, if you click on it once more, then you see that gamma is essentially the square of the, no, is the frequency squared times the mode capacitance times the beta I, which is the ratio between the coupling capacitance to the mode capacitance times the impedance. And then, okay, we need a small mode conversion to get the units right. But this is essentially how we compute gamma, and then 1 over gamma is our T1 limit. So this answers part one of the question. So we take an established formula, we compute the capacitances, and we get gamma. And then for part two, I
Mm,
don't quite know whether you could also use a driven simulation. I've not done this myself. Maybe there's a solution. In principle, we are also able to implement driven uh, S-parameter analysis with this design framework. In release number one, we did intentionally exclude the driven analysis, but we're working towards version number two right now. And there we would most likely include the driven analysis of S parameters again, such that you can also use them to optimize for kappas and decays, as you typically do with resonators. So in this sense, yes, once we've implemented the S parameter analysis with the driven mode analysis, then we should be able to also um, go that route that you asked for. Another question: is it possible to calculate the pi pulse duration of a fixed input power? If you know the coupling,
yeah, you need to know the G. Mm, if you
uh,
have the G value and if you know if you assume a pulse shape and you know the coupling, the G value between say your charge line and your qubit, then you have an expression for a given duration of pi pulse, what is the peak power that you need to apply. If you look at the cryogenic setup paper from Waldorf's group, they discuss this for a Gaussian pulse. But in our setup, I don't think we have yet integrated that part of the code. But maybe I should highlight here that in here now we have given the start and end of the pins which will control the distance between the charge line and the transmon pad, and that is the pins we use for this mini study, and the mode will be the qubit frequency mode, and we evaluate the capacitances um, for this. And now based on this, if we run this mini study, it will try to optimize for the T1 limit uh, of this qubit given how close the charge line is. And that is what goes in, say, actually, I should have been here. In here, where the variable to be optimized is the qubit T1 now.
all right. Shall we go back to the main example, the main file?
Yeah. Yeah.
Okay, now okay, we've generated the design. We've just set up the mini study. Um, the optimization target here in this case will contain the optimization target here will contain the get op target T1 limit via charge line position X. Can you click on this? Yeah. And you see it has a parameter type, which is a charge line limited T1. So we would specify a time. The mode involved here is the qubit mode. The design variable is the position of the charge line relative to the qubit. We can specify some design constraints if we find the charge line to be neighboring some other structures. And we would typically say that the closer we come with the charge line to the qubit, the stronger the coupling is, and this with a square. And this
Yes,
is
this is
this is our optimization. This is our optimization target. The bracket of all these five input information. Now we can basically set up the design analysis, which is done in the usual way. No surprises here. We take the mini study, we take the op targets, we take the design, and we just execute the cell. It's pretty much a standard cell that is identical for all mini studies that you want to execute. So I think Kunal already executed it, right?
yeah.
And then comes the time where we run the optimization. We did it already.
Yes. And I closed the answers file because I
Ah,
didn't comment this. But
all
okay.
right. All right. And here you can see that we compute the T1 limit for uh, multiple iterations of the solver, and it looks a little wiggly. And this has to do with the fact that we're probably not low pass filtering uh, this simulation sufficiently. So if we were to run this simulation again versus with a lower adjustment rate, we would probably find it to yield a smoother result.
Mhm. Should I update it? No.
Yeah. But I think we could also somewhat leave it at that point and leave this as an exercise to the reader, um, because all there's to see is that uh, you lower the adjustment rate and the result is more low pass filtered and it should converge nicely. Um,
Are there more questions here? Nothing in the chat.
um, just for everyone to know, every question that came up in this breakout room, I've noted on our side, and we'll try to clarify this in the documentation and also in the paper that we're writing right now. And we'll also uh, fix a small bug in the charge line in the capacitance simulation.
Okay, I can't really show that how it updated, but okay.
That's
The
fine.
final thing is this distance that is. But okay.
Yeah. Okay, but this was also just a small add-on to show you that capacitance simulations are also possible, and also more tailor-made examples such as computing kappa and computing T1 decays into a charge line are possible via capacitance simulations. And yeah, to say this once more, the driven mode analysis is coming back or coming into the open source release with the next version. That much I can promise. Are there more questions?
Mm, they have
Otherwise,
asked if other breakout sessions were also recorded.
uh, I'm not a Zoom expert, but I think so. I think so. And we'll make them available via YouTube and share them with you afterwards so that you can rewatch them and yeah, yeah, find the answer to your question uh, somewhere. Uh, All right. To me, this sounds like we're good here on this side. Um, if you don't have any more questions, I would wish you a wonderful weekend. Thank you very much for joining. It was fun explaining this to you. It was fun finding one or two bugs live in front of you. It was fun to, see that people are interested. Um, and I guess for us, it was a great experience to organize a webinar, something we've also never done before. So yeah, thanks. Thank you very much for joining, and I hope you take something away from this meeting. I hope it is that you're going to use this optimizer, or you at least like the idea. Um, and yeah, let's see. Let's see where we can take this entire superconducting circuit community in the future. I'm at least excited, and hope to see you at conferences and other occasions in the future.
Yes, thank you for your time.
Yeah. Thank you, guys. Thank you. Thanks a lot.
Now
All
you stop
right.
sharing the screen then.
Yes, I think we're good here. Thanks, Kunal. All right. I think it's coming to an end. I'll stop the recording.
Yeah.
Bye bye.